Fantastic. Wow. Okay, thank you so much. Really good to be here. Thank you, guys. Good to see you. Okay, so yeah, I'm going to talk about a work that I did together with Shafi and Guy Rothblum. Shafi Goswasser and Guy Rothblum many years ago, and kind of where it stands today. So, okay, so this is about proof systems. And I'll explain the Muggle part in a bit. But proof system, you know, classical proof system, you have like a piece of paper, whatever, you verify it line by line. You know, this was studied for thousands of years by mathematicians and so on. But actually, the way we think of proofs really changed dramatically in the mid-'80s by beautiful works that were actually motivated by getting zero knowledge. So the goal was to get proofs that reveal no information, okay? And to get that, they changed the model of a proof system. And instead of being like a piece of paper or, you know, gazillion number of papers that you verify line by line, now a proof system is an interactive process between a prover and a verifier. So verifier asks a question, prover answers, verifier asks a question, prover answers, and importantly, the verifier tosses coins. So it's a probabilistic proof. And what you want is the usual, what we call completeness and soundness. If the statement is true, if X is in the language or the statement is true, the prover should accept. On the other hand, if the statement is false, or if X is not in the language, then for any cheating prover, the verifier should accept with probability very close to zero. So it's probabilistic. We can't argue that it's exactly zero, but we want to be very, very close to zero. Okay, so this is interactive proofs. These have been really successful, even though they were defined for the sake of getting zero knowledge. Soon after they were proposed, it was shown that actually these proof systems are very, very powerful. And what I mean by powerful is you can take statements that if you want to prove using a classical proof, they're going to be really, really long, like exponentially long. But if you use an interactive proof, you can make them much shorter. So it's much easier to verify interactive proofs than it is classical proofs. So that was kind of, that's amazing. So we did proofs like a certain way all the time, but now actually, wow, look, we can verify them much, much more efficiently. Forget about zero knowledge, put aside, just the efficiency part. And more specifically, what was shown is if I want to prove to you that a computation was done correctly, like that a computation, an input X outputs Y, and let's say this computation takes time T and space S to run, you can convince a verifier where the verifier runs only in time that's proportional to the space of the computation. So essentially runs in time, more or less, the space time logarithmic in the time. Okay, so this is fantastic. It's much more efficient than we can do classically, but there's one caveat to that. And the caveat was, at least in this original works, was that, yeah, the verifier is very efficient, but the prover is grossly inefficient. So if you want to run this prover, it'll need to run in time basically 2 to the space squared. So crazy time, completely inefficient. Okay, so theoretically it was really beautiful, but it's clear we can't actually use this. So then we asked the following question: can we get such a proof where also the prover is, you can run it? Okay, so this is what's called a doubly efficient proof or interactive proof, where we want if the prover wants to convince the verifier of a correctness of a computation that takes, let's say, time T and space S, let's say as before, we want the prover not to have much overhead above just computing. Okay, so of course the prover needs to compute to get the output, it takes time T. But we want to, in order to prove, we don't want much overhead above that. You know, ideally even linear in T, quasi-linear in T, definitely not more than polynomial in T. Okay, so we want the prover to, and that's what we call, we want the prover to be a Muggle. Okay, the prover is also not a wizard. Actually, you know, in the original works, they even called the prover a wizard because he was like all powerful. But in real world, we don't have wizards. You know, we're all Muggles. Even the prover is a Muggle. And therefore, that's kind of the name of the talk. The prover should also be somewhat efficient. And of course, the verifier should be like extremely efficient. Okay. So let me tell you, actually, we do not know how to do this today. Okay. But even before, you can ask, why not polylog T? Why do we, let's get rid of the space also. Like, why can't we do better? And I just want to say, this is the best we can do. We know that the verifier must depend on at least the space of the computation. Okay, so this is the best we can do, but even this actually we cannot do. Okay, there's a beautiful result that gets close to it, but the verifier runtime is not polylogarithmic in the time. It's t to the epsilon for some small epsilon. So, we still don't know how to do this, but let me tell you what we do know how to do. And that's what I'm gonna talk about today. So what we do know is how to prove the correctness of any computation that can be computed by a depth D circuit. Now, I'll explain in a second what I mean by depth D, but essentially you should think of it as being computable efficiently viewed in parallel. Okay, so if you run it sequentially, it's very, very long, but in parallel, you can do it much more efficiently. That's kind of an intuitive notion for what the depth is. Okay, so I'm going to show you actually such a doubly efficient interactive proof for any computation that takes time t, but depth, think of depth much smaller, d. The runtime of the prover is polynomial in t, can be made very efficient, actually can be made quasi-linear in t, even linear, I think now, by many works that have been worked on this. And the verifier, it grows linearly with the depth of the computation. Okay, so it's good for bounded depth. Think of like small depth computation. And by the way, just as a side note, one can go from depth to space and vice versa, but the time, it doesn't preserve time. So any depth D can be space D, any space S can be depth S, but the time does not transfer nicely from one to the other. Okay, but this is the result, and let me now explain what it is and how we get it. Okay, so first, what is a depth D computation? So think of, we have a computation, think of it as consisting of addition and multiplication gates. We'll stick to the algebra the swastik had. So like, polynomials, think of addition, multiplication gates. And think of it as layered, circuit is layered, and the depth is the number of layers in the circuit. So the size of the circuit or the time is the number of gates, but the depth is the number of layers. So now I'm going to show you how to do an interactive proof. So think of, I have this really, really large circuit. Okay, there's an efficient representation of this circuit, but it's very, very large. And I did this computation. I computed each and every gate. Now I want to convince you of the output. So here's my circuit. I want to convince you that the output is 1. Okay, think of the number of gates here is huge. The depth is small. You're going to run in time the depth. I'm going to need to compute the entire thing. Okay, so let me tell you first kind of try how I'm going to do this. Okay, so we all know this circuit. There's some efficient representation. There's the input x1 up to xn. I'm going to compute all the gates. I got the output 1. Now I want to prove to you that the output is 1. Okay, you don't want to compute all the gates on your own. So how do we do that? Okay, so here's a first try. You with me? Any questions, by the way, before? Yeah, so my goal is to prove to you that a computation is correct. Okay, here it is. We're good. Great. Okay, so I claim the output is 1. You're like, I don't believe you. I said, fine. Look, I'm going to open the 2 children. You'll see that this gate is satisfied. If it's an addition, you'll see that the sum is 1. If it's a multiplication, you'll see that the multiplication is 1. Happy? Yes. Now, you say, okay, maybe 1 is false, so one of these children must be false. If the output is not 1, then one of these gates that I gave you is not the correct evaluation. Now, okay, so choose one. Let's say you said, okay, you know what, the left one, I think the left one is wrong. So I told, no, it's right, it's right. He said, prove to me. Sure, I'll give you the 2 children. Check the consistency of the gate. Now, if that left child was wrong, was not the correct computation of x, one of the children must be wrong. Guess which one is wrong? Let's say you guess the right is wrong. The right side is wrong. Okay, and there we continue like this, down, down, down. So for D, like the depth, yeah, until we get to now input gate, and then you know the input, so you check me. Okay, this is an interactive proof. You talk, I give you value, you choose one of the children, I give you the value of the children, you choose one of the children, good. Okay, so it is an interactive proof, but it's a bit pathetic. The reason it's pathetic, or why it's not that good, is because actually you catch the cheating prover with very small probability. So as long as in one gate you chose kind of the child that was correct, that the value in that child was correct, that's it. The prover can cheat from now on. So you always need to kind of guess the child that's incorrect. All like from 1 up to D. And you guess that with very small probability. So that's not good. But it does kind of show the idea behind this, what's called the GKR protocol. And the idea is, how do we make it work? So this is not good for us, but we want to do kind of amplification to make the soundness or to catch the prover with higher probability. And to do that, we do what's called soundness amplification. And now I'm going to thank Swastik for his talk, because how do we get this sound simplification? What we do is essentially me, the prover, I'm gonna not only compute the gates ahead of time, but also I'm gonna compute an encoding of each gate, of each layer. So I'm gonna compute all the gates. For each layer of the circuit, I'm gonna look at all the values of the layer, and I'm gonna compute an error-correcting code of this layer. Which error-correcting code I don't want to go into, but it's polynomial, essentially like Reed-Solomon, but a multivariate version. So think of it, I'm going to compute, take your points, and kind of do a low-degree extension, exactly like Swastik said. Okay, so I'm going to take each layer, compute kind of a low-degree extension of this layer. Okay, what's the point of this? Why am I doing this low-degree? So far, I didn't do the protocol. I'm just saying what I'm doing in my head. Now we're going to start the protocol. Okay. But let me first tell you why I did this error-correcting code. What's nice about this error-correcting code, as Swastik said, the error-correcting code has the following property. If one of the values is wrong, and I did the error-correcting code correctly, most of the values in the encoding is wrong. Almost all of them would be wrong. So before, when one of them was wrong and I chose one of them, I got something that's wrong with probability half. But if I choose a random, if the verifier, so sorry, you're the verifier. You chose one of the children, with probability half. You chose the one that I cheated on. But now you're going to choose a random point in the encoding. And a random point in the encoding, if I was incorrect, a random point in the encoding will be incorrect with very high probability. So that's what allows us to amplify the probability. That's really the basic idea behind the GKR protocol. So let me tell you actually, but now there's a question, okay, how's the reduction done? Like before it was very easy to go from one layer to the next. I give you the two children, you choose one of them. How is it done now over the encoding? So essentially think of it as follows. I give you the output, 1, I tell you it's 1. You're like, I don't believe you. Sure, here's the two children. Okay, look at the two children, you see consistent, but which one do you choose? You don't want to choose one of them because again, you'll be incorrect you'll guess with probability half, you'll guess the one that the value is correct, and then I'll cheat. So instead, you continue with a point in the extension, in the low-degree extension. And the error-correcting code has the property that this point will be incorrect, will be a false value with very high probability. And now I want to go from that point to a point in the layer below, to a point in the layer below, until I get to the input layer. In the input layer, you guys can compute on your own because you know the input. That's the basic idea. But then, of course, the question, how do you go from layer to layer in the encoding? And that's actually a bit more subtle, but really the only thing that's going on in this reduction from layer to layer on the encoding is really what's called a sum check protocol. Okay, that's it. It's just a sum check. I'll explain I'm not going to go into the details of a sum check, but I'll explain this point. But in general, here's the GKR protocol. You go from layer to, we run sum check, we run sum check, we run sum check, we run sum check, until the output, the verifier checks on its own. Okay. But now I want to say a little bit more about what is this sum check and what is this reduction? We're good? Questions with me? Great. Okay. So let's look at like a little part of this circuit. Let's say going from layer L to layer L minus 1, which is one layer below. Okay, so I already convinced you that, you know, the layer L, the value in some point, and then coding is some value VL. Now, let's say it's wrong, it's false with high probability. I want to reduce it to verifying a value in layer L minus 1, and that should be false also with high probability. So how is that done? So here's the observation. First of all, this error correcting code, the encoding, turns out it's a linear error correcting code. Okay, the low degree extension is a linear error correcting code, which means that the value VL is just a linear function of all the gates in that layer. So it's a linear function of the values of all the gates in that layer. Okay, now here's the point. I'm gonna encode this circuit, think of it as having only addition gates or only multiplication gates. Okay, you can easily encode a circuit in such a way. So now there's two cases. Either we're like in an addition layer, so all the gates are addition gates, or we're in a multiplication layer where all the gates are multiplication gates. Okay, if they're all addition gates, then now it means that the value VL is not only a linear combination of the value of the gates in layer L, it's also a linear combination of the values of the gates in layer L minus 1, because it's linear, because addition is linear. So you have its weighted sum of layers of values in layer L, but each value in layer L is a sum of 2 points in layer L minus 1. So you get that VL should be, like if you did it correctly, it's a sum, a weighted sum of elements in layer L minus 1. That's if an addition gate. This is exactly what a sum check allows you to do. It allows you to check if a value is a sum, a weighted sum of a lot of points. So again, I don't want to go into the details, but this really, the sum check really allows you to do this. Okay, and what you will get to verify the sum check, you will need to check, it will reduce to verifying an element in the low degree extension and the encoding in layer L minus 1. So this is really just a sum check. Okay. And again, without going into the details of what a sum check is. Case 2 is more interesting. Let's say the layer is full of multiplication. Okay, it's just multiplication gates. Here things seem to be complicated, and the reason it seems to be complicated is because now think each point is a multiplication of two elements. It's like a multiplication gates. It's each point in layer L. It's a product of two elements in layer L minus 1. So VL now will be a linear combination of products of two values in layer L minus 1. And so now you can still do a sum check, that's good, but it will reduce, because it's a product of two, you'll reduce checking VL to checking 2 points in layer L minus 1. Because it's a product of 2 points. And that seems like it's a problem because you went, yeah, I have it. You went from 1 point to check to verifying 2 points. And it seems like, well, if you go one layer below, you'll need to go from 2 points to 4 points, 8 points. It seems like this will blow up and it's a problem. And in the original GKR protocol, we took care of it by running an additional sub-protocol called what we call the 2-to-1 protocol. But actually later we noticed, actually you don't even need to do that. Actually, if you run the sum check a little in the right way, things don't blow up. Just do sum checks. And what I mean by that, what we noticed is that if you run the 2 sum checks, so the sum check protocol is a randomized protocol. The verifier tosses coins. If you run the 2 sum checks where the verifier uses the same coins, so you run them in parallel, the verifier uses the same randomness for both sum checks, actually you won't go from 2 points to 4 points, you go from 2 to 2. The number of points actually won't increase. So what is the GKR protocol? We go from points in the extension of layer L. Each time we run 2 kind of sum checks in parallel. The verifier uses the same randomness for both sum checks, and we kind of go layer by layer. That's basically it. So again, I didn't go over the details of the sum check, but modulo that's really what the GKR protocol is. Okay, so let me just say a bit the negative side, the problems with this protocol. And the main negative sides of this protocol is that the number of rounds grows with the depth, and the runtime of the verifier grows with the depth. So it's very interactive. For each point, we need this kind of to run this sum check protocol for each layer, and also the verifier, runs runtime can be big if the depth is large. Now, there's ways to overcome both. So for the round complexity, actually, because it's in this protocol, the GKR protocol, or in the sum check protocol, actually, all the messages of the verifier are just random bits. You can apply what's called the Fiat-Shamir paradigm, and you can make it non-interactive. So the Fiat-Shamir paradigm is a very famous paradigm, probably. Who's heard of the Fiat-Shamir paradigm here? Yeah, okay, so I expected many heard of it. So I'm not going to go into what it is, but it's a way of reducing interaction in public coin protocols. So when people implement this GKR protocol, they always use it, they implement it, they apply the Fiat-Shamir to it, so it becomes non-interactive. I want to say a few words about the Fiat-Shamir, because it's a paradigm for reducing interaction. There's a question if it's secure. In practice, it's always secure, so practitioners never worry about it. Okay, it was never broken, seems great, so continue to use it. In theory, we've thought about this question a lot of whether it's secure or not. And because if it is secure, we want to be able to prove it's secure. And currently, we're still kind of not there yet. We've invested a lot of our efforts on it. Actually, so it is secure in what's called the random oracle model, which is a very good proxy for security in practice, which is why you should continue to use it. But interestingly, we have counterexamples that show it's insecure. Now, these counterexamples are contrived, which is why you should still continue to use it. But it's interesting that we can't actually prove that it's secure in general. And moreover, even in the original SNARK construction of Kilian and Mikali, there are examples that show that the Fiat-Shamir actually fails even on this protocol. That it's like the protocol itself is not contrived at all. But if you use a contrived ingredients in it, then again, the Fiat-Shamir fails. So, the Fiat-Shamir is still, for us, we're thinking about a lot. I do want to mention, though, for the specific GKR protocol, we did manage to prove that the Fiat-Shamir is secure under standard cryptographic assumptions. So that was one thing that we've been working on. So that's kind of takes care of the rounds. Still, the verifier, the communication complexity or the runtime of the verifier grows with the depth. And that, is also, so what if it's deep? Now the verifier is not efficient. So even for that, people have overcome this barrier. And the basic idea, what you do, you squash your circuit. So if you have a very deep circuit, you squash it in the following way. Think of in the squash circuit, the input are all the values of all the gates in the circuit. So I'm the prover. I compute the values of all the gates in the circuit. But now I think of all the values of the gate of the input. And the circuit we're checking is that all the gates are consistent. Okay, so this is a very shallow circuit. So the depth is very small. It's like log. And now we run GKR on this. So I think this is often in practice what people do. The thing is, that's tricky, is that the input here is the values of all the gates of the original circuit. The verifier doesn't know what the input. And for GKR, the verifier needs to know the input. Now he doesn't know the input, so how do you do GKR? And the way people do it in practice is they add another component, which is what's called a polynomial commitment. There's another thing people done, which is assume an additional non-commuting prover. But mainly what people do is they add another component. It's called a polynomial commitment. And that I'm not going to go into what it is, but Fry is one way to do this polynomial commitment, probably the most efficient way to do this polynomial commitment. And if you use a polynomial commitment, you can get rid of the depth bound. Okay, so I will end here. Thank you very much.
So since Avi is not here, we do have a few minutes for questions if anybody has one.
Yeah.
Yeah, I was wondering that if the prover is going to compute the error correcting code for each depth, is it possible to be pre-processed or something like amortized at some point? Because it's a deterministic computation and the circuit is known to the prover.
Yeah, okay, good question. So the question was, can we pre-process The thing is, I don't see how to do that for the following reason. The circuit is known, but the values of the layer depend on the input. So for each input, even though the circuit is known, you have different values. So, you know, maybe if you run it on inputs that are related, so here's an example where you can amortize. If you run it on different inputs, but like here, let's say run GCAR on many, many inputs, and kind of the first part is like the values are the same for all the inputs and it differs kind of later. Then you would be able to amortize this. But in general, if you run it on different inputs, the values in each layer is very different, and I don't see how to, but that's a good, there are ways to amortize actually. I'll tell you, if you run many times, you can actually just do kind of one GKR protocol. So there is a way, it's not really to amortize the runtime of the prover, but you know, if you want to do many computations, like the depth doesn't really grow because you do them in parallel. So you can do a lot of, you know, GKR is good if you want to do a lot of computations in parallel, because then kind of the depth doesn't grow and the verifier becomes very efficient.
Would you mind elaborate a little bit more on the unknown input problem using polynomial commitment scheme
Yes.
over the squashed?
Good. Yes. So for the GKR protocol to work, the verifier knows the input. The verifier, because then the verifier needs to compute on his own, kind of then point in the encoding. Now, if I want to squash the circuit, let's say it's deep. So now, if my circuit is deep, I want to think of my circuit instead as a new circuit that takes the value, the input of the circuit are all the gates in the circuit. Okay, the value of all the gates. And what the circuit does, it checks that like all the, you know, that like all the gates are satisfied, that all the gate values are consistent with the gates in the circuit. Okay, but then how does the verifier know? He needs to compute a low degree extension, a point in the low degree extension and then encoding about these gates. So what do we do? So the basic idea, before we start the GKR protocol, the prover will compute like all these encodings and everything and send it to you. That's the only place where we use cryptography, by the way, in the GKR protocol. Before that, there's no crypto at all. The only place where crypto is used is I'm going to compute all these, like all the gates, actually an encoding of all these gates, and I'm going to send it to you via like a succinct commitment. Okay, so I'm going to kind of use crypto to kind of take all this information and kind of squish it down, and I'm going to send it to you before we start the GKR protocol. Now, I'm kind of bound. I assume that I can only open the commitment in one way. It's kind of binding. That's the property I want of this commitment. That's why I call it, I committed. I'm bounded. I'm binded to that specific value. Moreover, and then we run, and then you ask to open now you need to verify the encoding of the input. You tell me open, tell me, I don't know the input, but you committed to it ahead of time, so tell me what it is. That's basically how it goes. However, you need to ensure that that commitment includes like a correct encoding. Like maybe it's not encoding has a property. It's like low degree, you know, it's not just arbitrary. So you need to ensure that the prover didn't commit to an arbitrary values, but actually committed to some encoding. And that's where Swastik's kind of test comes in. You want to test that it's indeed a low degree extension. And kind of the fry is a very efficient way to test. So really how it works is I give you a commitment to an encoding. I prove to you that that what's committed is actually an encoding or close to an encoding. And then we run the GKR protocol. At the end, you need to verify a point and then coding. You ask me to open my commitment. And this commitment needs to be opened efficiently. And, you know, so that's very, very high level. But I want to say, I think most of the work that uses the GKR protocol, most of the innovation since the GKR protocol, which was in 2008, is in kind of finding better and better polynomial commitments. That's, I think, okay, I'll defer to the experts here, but I think that's kind of the point of like where the inefficiency usually comes in and where all the improvements came in. Yeah? Yeah. Okay. Yeah.
Thank you, Yael.
Thank you.